Swayam Prabha. Digital India. Educated India.
I welcome you to this course on flow through porous media. What we are discussing is the continuity applied to porous media, how we can leverage this understanding of continuity as we see in fluid mechanics to solve, to get a better visual of what all are happening in porous medium, assuming continuum to be valid. So, suppose in a porous medium we have a well and nearby we have a line source, then we have a boundary, then we have several things happening together, okay, and we are trying to find out flow will go in which direction. I mean, Darcy's law is fine, we can find if you have a unidirectional system, you can find out what is pressure drop and all these. Or the other way is we can solve this, we can put this in I, J, K and go by, we have already solved the continuity. But if you have several such, if you have a combination of all these flow elements in one place, is there any better way? Can we do it with some amount of finesse, this handling of, or at least the idea is that we want to get some feel, flow would be taking place from which direction to what direction in, or what kind of twists and turns it can make. So, for this purpose you must have noticed already that in fluid mechanics streamlines they serve this purpose very well. These streamlines, they call it stream tubes. So, in porous media also these application of streamlines and stream tubes, these are very common. In fact, this petroleum engineering and this oil and gas reservoir simulation people, they are constantly trying to find out how the streamlines would be, how the flow would take place to get better visual, because these are I mean numbers that do not appeal to us. If we get a better visual, that is very much wanted, and if we have a way to connect those visuals with the digital information, that is the best thing we need. So, that is why we will be defining these streamlines, potential lines, and of course, they are all tied, because streamline represents a particular value of a stream function. Along the streamline, the value of stream function is constant. So, we can toggle between digital information and the visual. So, this is something which we are taking our continuity to, the next level, which is in the form of stream function and potential function. So, let me start today's lecture. This is we are working on this mass continuity in Cartesian and cylindrical coordinate system, and our objective is to find out pressure equations and velocities. Now, we have this definition of stream function and potential function. So, what is this definition? First of all, the definition of stream function is something like this. We have these we have already talked about a velocity field, right? Velocity field is u I hat plus v j hat. Let us say we are focusing on a two-dimensional velocity field. So, it is u I hat plus v j hat. Okay. So, now the stream function which we are calling is psi, this stream function is defined such that u is equal to del psi del y and v is equal to minus del psi del x. So, this is so now what we are trying to do is this velocity field with two values of u and v. Instead of that, we are trying to put this entire thing into one package, which is psi, the stream function. Instead of calling u component, what is u component, tell me, what is the v component, you tell me. Instead of this, what is the stream function, you tell me. So, in one package, so the package is that u is equal to del psi del y and v is equal to minus del psi del x. What is the advantage of doing this? The advantage is that we have already said that if we have a, we call this a streamline. I have an obstruction here and I am seeing the flow taking place like this. So, we are having these. So, this is, so let us say this is the flow. So, these are basically the streamlines, the lines along which a paper boat will travel. So, what we said is that the tangent to this streamline defines the velocity at this point. Tangent to the streamline defines the velocity at this point. So, on the other hand, what do we see here? If we write this as u is equal to del psi del y and v is equal to minus del psi del x, what we see here is that what is d psi in this case? I can write d psi as del psi del x dx plus del psi del y dy. What is del psi del x? Del psi del x is equal to, del psi del x is equal to minus v. So, minus v dx, and del psi del y is equal to u plus u dy. Okay. So, what does d psi is equal to 0 implies? So, if I force, for the time being, if you assume that let us force this d psi to be equal to 0, what does that mean? If this becomes 0, then in that case we can say that this v dx becomes equal to u dy, or you can write dy dx is equal to v by u. Okay. So, dy dx is equal to v by u. So, what does this mean? I mean, suppose I tell you that streamline is a line along which psi is equal to constant. So, that means I can say streamline is the line along which d psi is equal to 0. So, streamline is the line along which dy dx is equal to v by u. And what is dy dx? The slope of this line. And so, every point the slope of this line, or in other words, you can write here as dy by v is equal to dx by u. So, that means dy by v is equal to dx by u. So, that means let us say this is the streamline and I have a section, let us say, which is ds. So, this ds is broken into dx I hat plus dy j hat, right. So, this segment ds is dx I hat plus dy j hat, On the other hand, the velocity has u I hat v j hat. So, we are saying dy by v is equal to dx by u. So, essentially we are saying that this tangent is same as it is showing the same direction as what is given by the velocity. There is other way to look at it also. I mean, if you want to look at it this way, it is that these tangent to the streamline and the velocity, they are in the same direction. You can write these as v cross ds has to be equal to 0. So, in that case you can write u I hat plus v j hat and take the cross product of dx. ds can be written as dx I hat plus dy j hat, that is equal to 0, and I cross j is equal to k. So, if you follow this, you will end up with this expression. So, essentially one can show, I mean, my point is that this, I am trying to say, on one hand, streamline is a line along, streamline is a line at any point. If you draw a tangent on this line, this shows me the velocity of this tangent shows me the direction of the velocity at that point. Okay. On the other hand, we are saying that streamline is a line along which the stream function psi is constant, where psi is defined in such a way del psi del y is equal to u and minus del psi del x equal to v. So, this is the definition of stream function we must make note of. Now, let us close this discussion on stream function, and instead we get to the potential function. Potential function, generally the genesis of this potential function is that we have, for the flow to take place, one needs a gradient in some form. I mean, just like that same, by the same token, we have we need the temperature gradient for establishing a heat flow, we need a voltage gradient to establish a current flow. Similarly, I mean, we said at the outset that the Darcy's law and everything, there we have a cause and effect relationship. We need a pressure gradient to have a Darcy flow. Now, what people have done in the fluid mechanics or also in other in porous media as well, that instead of putting instead of relying on pressure, because pressure is a different kind of term. So, just for this purpose, they prefer to define something called a potential, velocity potential. Just like you have voltage is electric, in the electrical sense it is the potential. Similarly, for flow purpose you have a velocity potential and we want to call it phi. So, this is, you will find that potential lines, which means that this potential function phi is constant, and isobaric lines where the pressure is constant, they in many cases, you will find in many cases they are similar, but people prefer to work with this potential function, because pressure in a true sense, pressure, the definition of pressure is not that if you have a pressure gradient then there is a flow. Pressure is not defined that way. Pressure is defined as, if you look at the definition of stress tensor, you will find that at a point in the stress field you can generate the stress tensor, and then the diagonal terms, which is basically sigma xx, sigma yy, sigma zz, which are the normal components. These, if you take minus of average of these diagonal terms, that is defined as pressure. And so pressure, definition of pressure comes from a different viewpoint. The definition of pressure did not come from, okay, if you have a pressure gradient then there will be a flow. So, for this purpose they prefer to have a different term altogether, which is potential. So, that is the origin of potential function and potential lines for that matter, along which potential function is constant, just like you have streamlines along which the stream function is constant. Now, when it comes to this potential function, I found there are some authors who prefer to work with, prefer to write the velocity as, let us say I have u and v. We said that v, the velocity field, is u I hat plus v j hat. So, this velocity u and v, they prefer to write these as u as minus del phi del x and v as minus del phi del y. What was u? You remember, u was del psi del y and v was del minus of del psi del x. So, you can see the difference between psi and phi. Now, there are some people who argue that this, since you are following, if you call the potential is the origin of potential is it is the gradient along which the flow will take place, just like along the temperature gradient the heat transfer takes place. So, you should impose a minus sign, just like we have in Fourier's law of heat conduction, we have minus k del T del x. But there are another substantial number of authors who did not put this minus sign, because the purpose is one and the same. I mean, you without minus sign still you can generate these plots. So, what we are doing in this analysis, we are not putting a minus sign. You can see here we are writing u is equal to del phi del x and v is equal to del phi del y. So, these are just like we have streamlines. By the same token, here we are talking about potential lines along which this potential function phi remains constant. So, what is the relation between streamlines and potential lines? You can see here very well that on one hand you are talking about del phi del x and the other hand you are talking about del psi del y. The line along which the stream function is constant, the line along which the stream function is constant. So, that line is basically is giving me d psi is equal to 0. So, d psi is equal to 0 means we have del psi del x dx plus del psi del y dy, that is equal to 0. So, what we had here is del psi del x is equal to minus v dx plus u dy is equal to 0. So, what that means is dy dx at constant psi, dy dx at constant psi, that is equal to v divided by u. Similarly, so slope of streamline, slope of a streamline which is dy dx at constant psi, because streamline means constant psi, that is equal to v by u, the velocity component in y direction divided by velocity component in x direction. So, at any point slope of the line is v by u. Whereas, if we look at the potential lines which says d phi is equal to 0, so that means you have d phi is equal to 0 means you have del phi del x dx plus del phi del y dy is equal to 0. So, now del phi del x is equal to u. So, instead of this you are writing it as, instead of this you are writing it as u, and instead of this you are writing it as v. So, what does this mean now? That this means dy dx at constant at constant phi. That means the slope of potential lines is equal to dy dx is minus of u by v, So, slope of streamline at a point is v by u and slope of potential line at a point is minus u by v. So, if we take the product of the two slopes is minus 1. So, what that means is, if we look at our understanding of basic geometry and coordinate geometry, we find that the product of the slope minus 1 means one is perpendicular to the other. So, that means if these are the streamlines, if these are the streamlines, I would expect the potential lines will be perpendicular to these lines. In fact, this makes perfect sense, because if these are the streamlines, let us say flow is taking place in this direction. So, what that means is that there must be a pressure gradient existing in this direction. So, I can say the pressure here and pressure here, they are changing. Okay. So, these are potential lines, which is for many for most of the purposes it is the isobaric lines. Okay. So, streamlines and potential lines, they are perpendicular to each other. This is something which we are supposed to know at this time. So, with this understanding of streamlines and potential lines, there is another major advantage of streamlines, which is that the streamlines are drawn in such a way. I mean, let me just clarify this. Let us say I see the streamlines are going and then coming close to each other. So, here I see the streamlines, they are coming close to each other. The streamlines are drawn in such a way, say let us say this is psi, okay. Psi is, let us say this is psi 1, this is psi 2, this is psi 3, this is psi 4. So, these streamlines are drawn in such a way that basically one can find one can say that the volumetric flow that takes place between the two streamlines is basically the difference between the two stream functions. So, volumetric flow per unit depth perpendicular to the screen between two streamlines, volumetric flow between two streamlines, per unit depth perpendicular to the screen, this is equal to the difference between the two streamlines. That means, in this case it would be psi 2 minus psi 1, basically it is delta psi. So, the flow that is taking place between psi 2 and psi 1, that is the volumetric flow that is taking place per unit depth perpendicular to this screen. So, that is equal to this difference in this stream function. So, if this is a value of psi 1, this is a value of psi 2, the difference between these two, that gives you the amount of flow taking place. Similarly, between psi 2 and psi 3, there would be some flow taking place, and that is the difference between the two stream function values. Similarly, for psi 3 and psi 4. So, what they generally do when they draw these streamlines, they make them intentionally, they make them, let us say the psi 1, the value is 1 meter cube per second per meter perpendicular to the board. Let us say I have that kind of unit. So, this psi 2 would be 2, psi 3 would be 3, psi 4 would be 4, like this. So, they are all equispaced. So, the difference there is always 1. So, I expect that it is the same flow that is supposed to take place. Now, when we see that these lines are converging to each other, what that means is that these lines, so there the velocity is increasing, because it is the same q that is flowing, 4 minus 3. Here also the same q that is flowing, 3 minus 2. So, it is the same volumetric flow rate, but now I can see over a smaller cross section compared to these. So, that means when I look from this point to this point, the velocity is increasing. This point to this point, velocity is even further increasing, because I see the cross section is decreasing here, but same flow is taking place. So, when I see the two streamlines, they are coming close to each other, that means the velocity there inside, the velocity is increasing. Whereas, when I see the streamlines, they are diverging from each other, that means the velocity is decreasing. So, by looking at the streamlines, one can make this kind of intuitive understanding of what is the what kind of flow is taking place there, and how or where the velocity is increasing and where the velocity is decreasing. So, this is one thing, one advantage of this visual. Another important point here one must make note is that no flow can cross a streamline. Why? Because we said that the tangent to the streamline gives me the direction of velocity at this point. So, if the velocity vector, I have a velocity vector, right, velocity field, which is u I hat plus v j hat, and that velocity field has the resultant is this, and this resultant gives me the tangent to this point. So, if this is the resultant, you cannot expect any component existing perpendicular to the resultant. That's the idea, right? So, in every point this is true, that means the tangent to this line and the velocity direction. So, you cannot expect any component existing perpendicular to this. So, no flow can ever cross a streamline at 90 degree. So, streamline cannot. So, streamline is a boundary line. I mean, no flow can be there perpendicular to a streamline at any point. Okay. So, that is also another take home message here from this. So, now what we are going to do with this understanding of stream function and potential function, we are going to merge the two. We are going to define something called a complex potential, which is a complex number. This is called Fz. This is a complex number which is equal to the value of potential function plus I is basically I square equal to minus 1. This is a complex number plus I psi. So, phi plus I psi. So, this is defined as complex potential, and we need to use this complex potential to find out the flow if we have different elemental flows present in one place. For example, a source, a sink, a line source, infinite line source of various types. If we have all together, what would be the net result? What would be the velocity? What would be the streamline? How would the streamlines look? Flow would be from which direction to which direction? So, we get visual as well as digital information, visual as well as analytical information from this study of this complex potential. So, I will continue this exercise in the next lecture. That is all I have for today, and that is all I have for this lecture. I will continue this exercise of I will continue working on this complex potential in my next lecture. Thank you very much. That is all I have for this lecture.